Welcome to the introductory lecture of the course VLSI Design, Verification and Test. So today is the introduction of the first lecture. So as we said, VLSI design today is conducted through a set of very sophisticated computer-aided design verification and testing tools. These tools take the design from a very initial and abstract idea of the functionality or behavior that we have in our mind. This can be an initial idea, non-formalized and hazy one. And then we first formally specify this idea in the form of say a flow graph or in a hardware description language, and then progressively take it down to a completely structural implementation in the form of a packaged chip. This is done through a very streamlined step-by-step manner. So the design process has evolved through years of research, and it has today become almost a science. So the objective of this course is to explain the fundamental algorithms and data structures that empowers these tools. So just a disclaimer at the beginning of the course that design, being a creative activity, can perhaps never be mechanized. Means you cannot expect that you will have a push button and from the initial design and you will get the final packaged chip. Human ingenuity will of course be required at each step of the design to understand how the different aspects of the design can be optimized to get what we want to achieve through the design. So why computer-aided design? So we were talking that today's VLSI design, verification and test is done through computer-aided tools. So why computer-aided design? The first answer is modern designs are too complex to be developed manually. In the 1960s, we had integrated a few hundred maybe device components on a substrate on the VLSI chip. And we have come today where there are multi-million gates per chip per substrate, and with that we have diminishing cost of transistor. Per transistor cost has diminished drastically over the years. So therefore on one side, because the number of transistors per chip has increased, we have been able to integrate more and more functionalities into the same design, on the same substrate, and hence the design has gone from simple to very, very complex and is almost impossible to be done wholly or fully by hand. On the other hand, this diminishing cost per chip per transistor has made it possible to devise hardware circuits, to make hardware circuits for possibly everything. So for today we have wearable devices, embedded devices to IoTs, and all these are in essence embedded systems which are integrated into a chip. So therefore the designer's salary and the time to market has become very important here, right? So to save such designer salaries, time to market, we need automated systems, automated algorithms which will take the design from the initial inception to the final package chip, hence CAD. The second important reason is that VLSI circuits are almost impossible to be repaired after the design, after it is designed. It is in hardware, right? So it cannot be repaired afterwards. So therefore there is a need to design almost zero defect designs. We need to create almost zero defect designs, and hence it has to be done through automated tools because humans are prone to errors. There has been larger and larger efforts. The third important reason is that we are trying to consolidate today many functionalities on a single chip, and we are progressively moving towards what is called system on chip, so that everything will be integrated into one chip. Why is this happening? Because it reduces the number of components per chip, it reduces the number of components, so the number of different chips that you require. It enhances performance, faster chips, because interconnection between chips or inter-chip communication will be always slower than intra-chip communication. This also reduces design cost in packaging and interconnection, because you are now packaging many things into a single chip, and it also improves reliability, because now always interconnections introduce errors in between. If you see today, if you see as an example this trend towards SoCs, we can take the example of a mobile phone. Say, today's mobile phones have processors within them. Obviously, a mobile phone will require a processor, and will most probably be a reduced instruction set architecture RISC processor. But along with that, it may need specialized DSPs, digital signal processors, for say voice and image data, and special instruction set catering to signal processing, other different types of signal processing. It will have RF circuits, radio frequency circuits. The mobile device should be able to communicate to the outside world, so it will require RF circuits. It will require analog components. So communication is basically an analog aspect, so therefore it will require analog components, digital to analog converters, analog to digital converters, all within the same chip. But it may require custom digital units. For example, if you need to do high performance encryption, decryption of image data, you may need to design an ASIC within the chip. So ASIC meaning application specific integrated circuits. So we should understand there is a subtle difference of these ASICs with ASIPs, which are application specific instructions and processors. The subtle difference being that although ASICs can have controllers within it, it will not include programmability. Programmability will only be an aspect of ASIPs and not ASICs. Okay, so it can also have MEMS or microelectronic sensors, because it will have different types of sensors, so pressure sensors, temperature sensors, proximity sensors, etc. So therefore, we see today that in our mobile phones today, the same chip includes a lot of functionality together, and may be regarded as a system on chip. And such system on chip, there is a proliferation of such system on chips today, and hence many functionalities are being included. Such designs are very complex, and we need computer aided design for that. Also, CAD provides a systematic step-by-step design procedure, as we said. So it will progressively take the design from one step to the next until the final chip is final chip is produced. And hence there is a necessity of CAD here. Also, higher integration, as we said, many transistors within a chip, higher integration will lead to huge power dissipation, because all these transistors within the chip, each of them will leak power, and hence there will be huge leakage power, and correspondingly we will have hot spots generated within the chip. And the heat today can be close to the heat that is generated with today's frequency at which these chips operate, and with the number of components in the chip, it could be that almost compared to a rocket nozzle. And hence people have devised ways, design methodologies by which the designs will be aware of the power consumed and the hotspots, and the design will be optimized accordingly. So there is a focus towards low power design strategies at each stage of the design. There is an increasing trend towards fault tolerant designs as well. So today we have safety critical embedded devices. For example, wearable healthcare devices. And manufacturing these chips with very specified levels of reliability is extremely essential. For example, if we take the example of a pacemaker, say today, it must be able to respond to very quickly with respect to say a missing heartbeat. So therefore performance is extremely essential in the design of this pacemaker. With that, this pacemaker will be placed where? Inside the heart. So therefore, it has to be small in area. So we understand that when we try to increase performance, we need to parallelly do many things, and doing things parallelly means we need higher area of doing that. However, a pacemaker cannot consume a lot of area as well. It has to be low in area because it has to be placed within the heart. It has to consume low power. Why? The reason is that it has to run for years together within the heart. So therefore it cannot consume a lot of power. So therefore it has to be power efficient. It has to efficiently utilize the battery's power. It has to be fault tolerant, obviously. It cannot suffer a fault being placed within the heart. So therefore it has to be highly reliable. And hence high reliability also means that these chips need to be easily verifiable, easily testable, and most importantly, last but not the least, it has to be low in cost so that it becomes affordable to the community. So what we are trying to say is that today's devices will require a whole lot of design optimizations to achieve at the final product. And for such complex designs, computer-aided design is extremely essential. And so what we understand is that, therefore we understand that at each stage of the design, we have different alternatives of the design, right? We can be very efficient on area, we can lack on performance, all these things. And it gives us a very big design space, which means that there are many possible solutions, many possible solutions within the given total space within which the solution can lie. And finding an optimal solution from this enormous set of feasible implementation choices almost always will require computer-aided design. It cannot be done by hand, and hence computer-aided design. Thus, with a basic understanding why computer-aided design is required, we come to the end of module 1 of this lecture.